So I'm Stefan Fassbinder from DKI, the German Copper Institute, a member of the Worldwide Copper Alliance, and I'm going to tell you something about electrical conductors today. Now, which actually is the situation that we have. There is quite a number of materials that are regarded as electrically conductive, but in the end, unfortunately, there is one slide missing here. Silver and gold are missing. And the best conductor you can have is silver, and it is closely followed up by copper, which is only 6% after. Then comes gold, then a bit of a gap, and then aluminium. Now, silver and gold shoot themselves out via the price, whereas I would not like to discuss copper prices today. And so only copper and aluminium remain left over as a viable conductor material for technical purposes. Now, you would probably assume that there is some competition between copper and aluminium, but it is, in our view, not really so much. The other properties of copper and aluminium beyond the electrical conductivity are so different that in most applications that you can think of, it is more or less clear right from the start which of the material, copper or aluminium, is the more suitable one. And there is a relatively small overlap where a competing situation may occur. One of them is electric motors, the rotors of electric motors, which have usually been cast in aluminium and can now also be cast in copper. And one overlapping range is, say, bus bars, which can be made of aluminium and copper. Transformers are wound aluminium or copper, depending on the actual price situation in the market. But in most situations, it is clear right from the start which material to choose. And beyond aluminium and copper, there are some other materials. We have steel for earthing electrodes, and we have other technologies which do not need any conductor at all. For the communication technology for electronics, we have fiber optics as an alternative cable, which is no electric conductor. We have radio transmission as a wireless means of transmitting signals. And for instance, we also have the new permanent magnet motors, which do not contain any conductive material either, which contain a magnet instead. But that is largely it. Now, what really is conductivity? Imagine a copper wire 1 meter long and with a cross-sectional area of 1 square millimeter. This has an electrical resistance of 0.01724 ohms. This is measured at 20 degrees ambient temperature. This means if you apply a voltage of 0.01724 volts across the ends of this wire, then a current of 1 amp will flow through it. And this means that the specific resistance, which is the resistivity of copper, is 0.01724 ohms times square millimeters per meter of length of wire. The inverse value of that is 58 meters per ohm and square millimeter, which is the specific conductance or the conductivity of copper. This means the other way around, when a current of 58 amps is flowing through the wire, you will measure a voltage of 1 volt across its ends. This is a theoretical experiment because you would need to keep the temperature at 20 degrees Celsius while carrying out this experiment, and that may become difficult. Now, you can enhance the wire from 1 square millimeter cross-section to 1 square meter, if you still want to call this a wire. It's a cube now, but this enables you to short out 1 meter in the equation, and the value will then increase by a factor of 10 to the power of 6. Now, with 1 ohm equal 1 volt per amp, which is the electrical resistance, the unit for the electrical resistance, or 1 Siemens, which is 1 amp per volt, the unit for the electrical conductance, the conductivity of copper is then 58 times 10 to the power of 6 meters per ohm and square millimeter. Now, you can short out 1 meter, and then it is 58 times 10 to the power of 6 amps per volt and meter, or 58 mega Siemens per meter, and this is defined as 100% IACS. This is the International Annealed Copper Standard, and this has been, so to say, defined as the rated conductivity of copper ever since 1925 in the IEC standard 060-028. Now, technical conductors which you procure today will have a conductivity of about 101% IACS if made of copper, which is equal to 58.51 megasiemens per meter. This is reached when you have a purity of the copper of about 99.98%. As you will soon see, the purity of the conductor material is the crucial parameter for reaching a good conductivity. In physics textbooks and other tables, you may find a value of up to 59.77 megasiemens per meter, which would be sparsely more than 103% IACS for really high purity copper, the so-called 6-digit copper, which has 99.49%. For aluminium, the corresponding value, the maximum value is 37.66 megasiemens per meter. With monocrystalline copper, you can even reach a tiny little bit more than 60 megasiemens per meter, or 103.5% IACS, more or less. But that is really the end of all technical opportunities. For technical aluminium, the corresponding value is 35 megasiemens per meter, or 60.35% IACS. So you see here that also aluminium is plotted and compared against copper, and copper is the material not only of choice in most electric applications, but also the benchmarking material. Now, here comes the affair with the alloyed elements. You see here on the right the plot for copper, and you see here that even minute constituents which are added to the copper as alloy elements will dramatically reduce the conductivity. The best thing to alloy into copper is silver, which enhances the mechanical properties very much and has the least impact upon the conductivity. One of the worst is, for instance, silicon, what else, the manganese, phosphorus. Phosphorus is very bad, and sulfur is the like. Sulfur is unfortunately not on this plot here, and it remains to be noted that we have a range from 0 to only 0.3% mass percentages of quantity of alloyed elements. Now, the effect is not so dramatic with aluminium, as you see here. You have here a range up to 1.2 percentage points, and you see that some elements really have approximately no impact upon the conductivity. Some have a considerable impact, but still much less than we have for copper. Note that we have here 60 megasiemens per meter, and that is 35. And this scale also doesn't match that one here. So this scale for the aluminium is wider, and you see that the impurities are by far not that crucial and that dramatic with aluminium, but with copper, the purity is the criterion out of all that for the electrical conductivity. Now let's make a little consideration in between, which leads us a little bit away from the topic, but which appears quite interesting to me. The question is, how fast really is the electrical current? The following thoughts and calculations lead you to perhaps somewhat sobering result. It is normally thought and said that electric energy propagates at the speed of light, which is quite fast. But that is not really true. This is only the shock wave, and it is not the actual motion of the electrons. Now, if you consider that one copper atom has 29 electrons, and only one of these is mobile, one electron can change to a neighboring atom and thereby enhance the electrical conductivity of copper. Now, 1 mole of copper, that is the molecular weight or the atomic weight, the atomic mass in grams, that's 63.546 grams. In the case of copper, or respectively 7.116 cubic meters, and this amount of copper contains 6.022 times 10 to the power 1023 atoms. This is Avogadro's constant. This is always so with all materials. When you take the molecular mass and you add the unit grams, then you end up with this number of atoms or molecules respectively in that said quantity. Now from here on, you can go on calculating. Then 1 gram of copper, hence, contains 2.7 something times 10 to 23 electrons, out of which 9.477 times 10 to 21 are mobile, can change to the neighboring atom. Then 1 cubic centimeter of copper contains 8.4 times 10 to 22 free electrons. Let's go down to 1 cubic millimeter, then it's 10 to 19, and the current of 1 amp, you must know, always means that at a particular point in the wire, 6.24 times 10 to 18 electrons pass by. This is the inverse of the elementary charge of 1.9 times 10 to minus 19 amp seconds or coulomb. At 16 amps in a home installation wire, in a building wire, size 1.5 square millimeters, this yields a speed of the actual motion of electrons of 0.8 millimeters per meter. That is not really so much. When a short circuit occurs, it may increase to 50 millimeters per second, but that's really all. So electricity is not really very fast in physical terms. Now, we often speak of conductive materials, but, well, what is considered conductive? Quite a lot that is very, very much less conductive than those materials which we call as metals. You see here on the left side are a number of metallic materials and the respective resistivities of these. And here on the right side you see other materials which are normally also considered conductive. Seawater or tap water, distilled water, and there's quite a difference between these, and particularly quite a great difference to the metallic materials. Note that we have a factor of 10 to minus 6 on this side with each of these figures, nothing like that on the right side. So we have something between 8, 9, or 10 orders of magnitude between the materials on the left and on the right. So the classical electrical conductor must be a metal. Now, is there really hardly any competition between copper and aluminium? To some degree, of course, there is, but as I say, the differences are, the other differences are quite great. When you look at the density, the ratio is 3:1, copper against aluminium. The conductivity, as mentioned, is 3:2. Now, the price, well, the prices are very volatile, but right at the time, they are roughly 4:1 of copper against aluminium. And to see this in relative terms, the same quantity that you need for a certain purpose, then you end up with a ratio of 8:1. Actually, you cannot compare the same mass or weight to compare the quantities of the metals, but you must compare the volumes, because the cross-section is decisive. And on top of the cross-section, you have to compare the conductivity. Conductivity is only 2/3 for aluminium, so you have to multiply the cross-section by 3 divided by 2, and then you arrive at a factor of 8 for the price that you have to pay for an equivalent conductor. Now, that looks appalling, but still, in most applications, copper is the preferred material. Why is this? For one, while aluminium is rather malleable and can easily be shaped and reshaped, it is not quite as malleable as copper. The ends of solid wires installed in walls tend to break after several times of bending to and fro. And aluminium is a very unnoble, the opposite of a noble metal, and it oxidizes very quickly at the surface when exposed to air. The oxide layer is hard and solid, but it is not electrically conductive. It's an insulant, so it hampers the conductibility. And the third point is that aluminium tends to long-term flowing. That means the material is fairly soft, and it under high pressure, it yields. It tends to yield, and contacts once fixed become loose over time and have to be re-screwed once a year or so, and that is not practical. Now, under the present price situation on the copper market, of course, we observe some substitution of copper with aluminium, but sometimes it also goes the other way around. You may have heard the presentation about the high voltage and extra high voltage overhead lines, which can now also be made out of copper. This is, of course, only for a niche application, because the higher cross-section that you need for an overhead wire doesn't matter much, doesn't disturb anybody, while the higher price as well as the higher weight of the copper line does very well hamper its use. Therefore, normally overhead lines are always made of aluminium. But there are situations now in the present days with the energy turnaround and the use of renewable energies that sometimes you need new lines, but you have no space, so it is very difficult to get permissions for new lines, and then the upgrade of an existing line is an option. And in these cases, the copper conductor can help. These conductors are actually made of a so-called copper microalloy. There is much less than 1% of alloyed elements in there, so that the conductivity remains considerably higher than that of aluminium, but the material is very hard, has a high operating temperature and a low sag, and therefore can be operated at temperatures up to 180 degrees Celsius, while aluminium goes only up to 80 degrees Celsius. Now, it is not normally that we produce higher losses, but in those situations where such a high load, a peak load occurs only 100 hours a year or so, the copper conductor is really a solution where an extra line cannot be installed. Now, please do not confuse these two standards. I mentioned this IEC 60028 from 1925, where the rated conductivity of copper was fixed for the first time, while we now also have the IEC 6228, which standardizes cables for installation in buildings and others. And it also includes maximum resistivities for each cross-section rating of cables. That means 1 kilometer of cable of the respective type of cable has a maximum resistance, and these maximum values for each cross-section are calculated with a conductivity of 55.5 megasiemens per meter for copper and 32.5 megasiemens per meter for aluminium conductors. Now, in fact, the conductivity of copper nowadays is 58.5, and then I think you can imagine what the cable manufacturers will do. In fact, a 16 square the cable has only 15 square copper in the end, but it serves the same purpose. Well, so much about copper and aluminium, but sometimes we also encounter other materials serving as electrical conductors. First one is steel. Steel is sometimes used as an electric conductor because it is sitting there anyway. The typical example herefore is the rails for railway lines, and steel is really made for and used for its high mechanical strength and is not a good electrical conductor. But if you compare the cross-section of a trolley wire against the cross-section of the rail, then the cross-section of this rail is so much larger that it does very well serve as a return conductor, because this facilitates the use of the rail as a return conductor and makes it easy to operate railway vehicles electrically, while on the road we still have great problems. You may wonder why you see a piece of cable here that connects this piece of rail to this piece of rail. Well, that is because the rails are the return conductors for the current. The second one is carbon. Carbon is also electrically conductive, far less than metals, but it has some properties that make it suitable for some applications. We have the coal electrodes in electric metal melting furnaces. We have contact pieces and pantographs, which are also made of copper. And as you see here, the coal brushes for commutator and slip ring machines for electrical motors and generators. You see here that, well, the conductivity of copper is 58 megasiemens per meter, and that of coal is only 25 kilosiemens per meter. This little piece of coal here, which is about 15 millimeters long and 64 square millimeters large, has the same resistance as this spring made of a copper alloy, which is 300 millimeters long and just 1/8 of a millimeter in cross-section. But still, these two have the same order of magnitude of resistance. Sometimes, to find a compromise, such material is used for slip rings and the like, which is a compound material out of carbon and copper, and therefore yields a compromise between the properties of copper and those of carbon. The third one is electrically conductive plastics. Now, electrically conductive plastics as such, the so-called intrinsically conductive plastics, do not really exist, or hardly any of them at all. Nearly all of them are made conductive by supplements and additives, and with fillers such as stainless steel flakes or steel fibers, sometimes silver-coated glass boards are used, or graphite or soot, which is mixed into the plastic and therefore makes it a bit electrically conductive. The share is limited to a few volume percent because you want to use the properties of the plastic, not those of the conductive material, and hence the conductivity of these materials is between 4 and 14 orders of magnitude lower than those of metals. Actually, they are not meant to be used as electrical conductors. They are used for applications where a tiny little bit of conductivity already suffices to serve a certain purpose, for instance, shielding. Intrinsically conductive plastics, where the plastic itself is conductive, are neither meltable nor malleable, and they are not dissolvable, so they are impossible to process. They are sensitive against oxygen, all of them, and they lose conductivity when exposed to air. Still, I found a publication, even by IEC, some years ago, titled Energy Grids 2050, where some visionary from Brugg Cables in Switzerland draws a fantastic picture of an electrical world with electric power cables, high voltage, extra high voltage lines, and low voltage building wire, all made of conductive plastics. But I couldn't trace anything of this in the internet, and I asked back with Brugg, and they said nobody knows anything about it. And the employee whose name was given here has long left the company. So that was it. The fourth electrically conductive material is liquids, the so-called electrolytes. Also, these also have very low electrical conductivities compared to the metals. I've plotted them here again, so that you can see the difference. Mind the 10 by minus 6 on this side, which is missing on this side. But these materials are very important for all applications where electrical energy is stored or generated in a mechanical manner, as say batteries and accumulators. Here they are needed, and actually the length of the conductor here is very, very short, just 1 millimeter or some few millimeters, while the cross section is thousands of square millimeters. In a wire it is vice versa. Therefore the electrical conductivity in this case suffices. The fifth type of conductors are the so-called superconductors, which lose all electrical resistivity below a certain temperature. Now, for many decades, this temperature limit was around 4 Kelvin, say minus 269 degrees Celsius, which limited their use to some very special applications. Until in 1986, I think it was, that so-called high-temperature superconductivity was invented, which means that it's not, you don't need 4 Kelvin, but already at 100 Kelvin, you can reach superconductivity with certain materials, but which is still minus 170 in degrees Celsius. Now, there are some applications which are enabled by such technology, by such conductors, which are totally impossible to make with copper or aluminium, even with silver. But these are quite sophisticated and difficult to explain to politicians. So the Trade Association of the Superconducting Industry in Germany, which has been founded a few years ago, requires that politicians take care of their technology, and they want support, they want frontier technology, they want 100 references being built and financed by public subsidies. Now, how do you get the politician to pay some public subsidies? You must say this here saves energy or saves the environment. Then you will get subsidies, otherwise not. And that is what they try. So they always try to tweak their applications in a way so as if they did save energy. Now, do they really save energy? Oh yes, when you read the publications, a superconducting generator in a wind turbine can save up to 50% energy. And you read the article and you wonder how that can be, and then you find out that they mean 50% of the losses in the machine, which are about 2% in the case of copper. So in total, 1% of energy is saved. But put into a relative term, you can call it 50. And they also try to promote superconducting high voltage and extra high voltage cables. And I always wondered how much energy you need to cool them down permanently to 100 Kelvin, 90 Kelvin, 80 Kelvin, which is their operating temperatures. And it took me years to find out finally that it was about 50 to 60 watts per meter which you need. Now, I calculated the losses in a conventional cable, and I ended up with something around 50 to 60 watt per meter at full load. And when you halve the load, then the losses, ohmic losses, of course, drop down to 1/4. And when the cable is running energized but without any load, then there are hardly any losses at all. While the cooling demand in the superconductor will always be there. Now, I wonder where the savings is. Actually, it is not there at all. As an aside, if you look at such a high voltage superconducting cable, it looks very similar to a conventional cable. You have a copper core here, which takes over the current in case the cable should become overloaded or too warm, and then the superconductivity breaks down. Then for a short moment, until the current is attenuated, it has to flow through the copper wire. The actual conductor is this here. This is one phase, this is the second phase, and this is the third phase. Now, they even dare to tell you, well, we still save 50% of energy. And then I say, well, if you double the cross-section of a copper conductor, they also save 50% of energy. Then this is why there are a lot of projects around in the world where the superconducting cables are tested, but there aren't actually any long lines. Why should you make them? The most recent application of conventional copper cable I came across is this message from ABV. They now released a DC undersea cable for 525 kV DC. So long 400 kV was the maximum voltage for DC transmission. Now this cable transmits a power of 2.6 gigawatts over a distance of 1,500 kilometers at a loss rate of less than 5%. Now, when you go back to the superconducting cable of this, with these dimensions, then 1,500 kilometers of cable need to be cooled down to something below 100 Kelvin at a power demand of a fraction of, well, what is it, 5% times 2.6 gigawatts, which is 52 megawatts, and that is about 36 watts per meter. Now, a fraction of that should suffice to keep the cable code before you really save anything, and that is, of course, not the case. Now, the sixth type of application is not to use any conductor at all. You frequently read about wireless energy transmission, wireless messaging and IT is long known, but to transmit energy without a conductor seems somewhat difficult. This strange company, Whitetricity, lives on that, although I keep on wondering what they really live on. Probably on adverts, because they lure a lot of clicks onto their website, and perhaps because they charge you $500 for a little demo which contains nothing more but a small LED and a small coil of wire, the copper wire, and their congenial recipe, they say, is that they use resonance instead of induction. Well, of course, in the end, it is induction. When you study what they do there, they use a wire coil for sending and a wire coil for receiving, and that is, of course, induction. We use resonance instead of induction is like saying this car runs on wheels rather than on petrol. But, well, you can build up a resonant circuit and let the energy oscillate around in a circuit between a capacitor and the reactor, sure. But again, you cannot let the energy oscillate in the resonant circuit and at the same time draw it out. That is not possible. As soon as you draw some energy out, then the oscillation will be attenuated. Now, as I said, they sell you some expensive demos which operate with LEDs. Pure fluke that nowadays we have LEDs and they are quite popular. Because LEDs, other than incandescent lamp, already produce some light at minute power input. Let's see here. We use a small LED here, and we apply 2.4 volts and 39 microamps. That's 100 microwatts, more or less. And we turn off the light, and you see some light. So what you get here is the evidence that indeed electricity has transmitted a power of 100 microwatts. Isn't that fantastic? Oh yes, it isn't. I tried to rebuild the whole technique back home, and I found out that it takes some 9 VA to transmit a power of 0.8 watts. If you use the transmitter coil, which is this wire here, this spool of cable, and this is the receiver spool. I use a frequency of 6.8 kilohertz here. Couldn't do more. Practical frequencies may be higher, but that doesn't really help so much. You see here that the input of 0.8 watts is in fact enough to make this tiny little torch bulb shine a little bit. It's rated 0.3 watts, so that is about 0.1 watt what you see here. So in fact, when the two coils lie side by side, then a fraction of the power is in fact transmitted over into the receiver coil. And this here, let me see, this here is the capacitor which I use to build up resonance. And in fact, yes, the resonance principle did work as long as you don't charge the resonance circuit, as you see here. Now, this is the calculated, the calculation, the theoretical calculation of what I just did in practice. You have a resonance circuit here, which is oscillating, and here I assume that 99% of the energy remain oscillating in the circuit, and just 1% per period is drawn out to make use of it. Then the amplification of the power at the point of resonance works indeed. That is quite significant. The red line is the effectiveness with resonance, and the blue line here is the effect if I used the coils alone without a capacitor. Now if I draw out 22% each time, then it looks already much worse. And now I say 50-50, say 50% of the energy remain oscillating in the resonance circuit, and 50% are drawn out every period. Then you have hardly any difference left at all between the resonant case and the standard case. So what? But the company lives on it. And as an aside, I really wonder what is wireless here. Yes, if you build two of these big coils here, a thick wire, quite a number of turns, and a very large diameter of the coils, and you use a high frequency which may range into the radio frequency and cause disturbances there, then it does work, yes. But what does wireless mean when you look at these coils? It takes obviously quite a bit of wire to replace a short, thin piece of wire. By the way, the technique is not new. It is since 30 or 40 years we have these tiny little accumulator-fed toothbrushes, and when the battery is being charged up, it uses 1.3 watts. When the battery is full, then it still uses 1.3 watts. And when you remove the toothbrush from the holder, then it also uses 1.3 watts. What I calculate here is an efficiency of 15% during charging, and at the mean annual is less than 1%. So whether we want this, I'm not quite sure. With inductive vehicles, that is a bigger application, and one where more care is taken of the efficiency. They already achieve 90% efficiency with wireless charging, and they hope for 95% in the future. Now, while this sounds good, it still means that over 1/100th of the distance, you still have 100 times more losses than with a conventional cable. So I think it's still a bit tweaky with the wireless techniques. And once again, back to carbon. From time to time, you start reading strange things about carbon nanotubes, which can reach fantastic properties and values, but in a way, they really do not hold. I heard only today that there is a new application where the carbon nanotubes could make it, and in fact have a higher conductivity than copper wires, while in this website that you see here, nothing new really moves, and I wonder what it is all about. It has remained static for a number of years. And the conductivity that they give here, 0.34 watts ohms per meter, that is really not so fantastic. Well, this brings me to the end of my presentation, and I'm open for questions and discussion now. And as an aside, this chapter about the conductor materials is the first one we now have in English available on our website of the German Copper Institute.